Hello students, welcome back to lecture series on linear algebra. Guys, in my today's video I'm gonna explain to you all eigenvalues and eigenvector, our main topic from this chapter. Already in my last lecture guys, I explained here some of the basic prerequisites like a Cramer's rule, synthetic division, how we can use this one, okay, that I explained in my last lecture. If you want to see, go and check in my last video. In my today's video guys, I'm going to explain to you all complete detailed understanding of eigenvalues and then eigenvectors. Okay, so without further ado, let's get dive into our today's lecture. Okay, what actually the eigenvalue are certain numbers or scalars, okay, associated with the square matrix, okay, mostly which are having application in population dynamics, electrical networks, chemical reactions, okay, and mostly like engineering field. These concepts are having a lot of applications. Okay, so let's start what actually the meaning of eigenvalue. Okay, consider that A is a square matrix. Okay, square matrix means which are having row and column equal, okay, m by n, but m which is equal to n. Okay, consider the square matrix, okay, which is a m by n. Okay, and again consider one of the vector. Okay, vector already we learn in a linear combination. Okay, for a linearly dependent vector, independent vector, there we learn vector. Okay, so we denote vector as x, okay, capital X, and which can be written as a column matrix x1, x2, x3, xn up to the so on. Okay, so this one is the square matrix. Okay, this one is the vector. This one is square matrix, this one is the vector. Okay, and consider that one of the variable, like I consider as a lambda. Mostly we define lambda as a eigenvalue or a characteristic value. Okay, consider this eigenvalue. We denote lambda as eigenvalue or characteristic value. We denote lambda as eigenvalue or a characteristic value. It is like some scalar or like some constant. Okay, so we are having three given conditions here. Okay, first A is a square matrix, vector x is given vector. Okay, and using this square matrix you have to define lambda. Okay, once you get the A square matrix vector eigenvalue which is a characteristic value, you can define eigenvector easily. Okay, eigenvector easily. Okay, so lambda is eigenvalue, A is a square matrix, x is a x is a vector only. Okay, and then we write eigenvector, okay, of the matrix A. We write eigenvector vector of matrix A. Okay, matrix A means A is a square matrix. Okay, we write eigenvector of a matrix A with respect to lambda. Okay, lambda as eigenvalue. Okay, some constant value as a lambda. We write eigenvector of matrix A with respect to lambda and vector x as Ax, which is equal to lambda times x. Okay, what is this? X is a capital X. Okay, this capital X is a vector, A is a square matrix, and lambda is the eigenvalue. Okay, eigenvalue or characteristic value. I'll explain to you all how to find out the eigenvalue in my next lecture. Okay, first of all understand how the process works. Okay, so x which is equal to lambda x. Okay, this one we define as eigenvector. Okay, if A is a square matrix, obviously x we know that. How we write this x, capital X, we write this vector as a column matrix. Okay, x1, x2 up to xn. Okay, this one is the way we define x as eigenvector. Okay, x is the eigenvector. The number lambda is known as eigenvalue or characteristic or latent roots. Okay, this one eigenvalue, characteristic roots or latent roots. Okay, eigenvalue, characteristic value or latent root. Okay, or latent root value. Okay, so you can call any one of it, okay, as a lambda. Okay, so now we have to define eigenvalue. Okay, we have to define eigenvalue. How we can find the eigenvalue of our given eigenvectors? Okay, so we have eigenvector x which is equal to lambda x. Okay, so what do we do? Try some operation on it. Okay, that means if you write identity here into the a, identity here into the lambda, nothing matter. Okay, it will give us already the value which as it is here. Okay, so we can write this one as a x as a lambda times identity into x. Okay, lambda time identity into x. Okay, so take this one to the other side now. So what we get? Ax which is equal x minus lambda times ix which is equal to 0. What I have done, this positive lambda ix, I take it to the other side, I got the negative lambda ix. Okay, so what we can do, we can take eigenvector x, vector x out of this two numbers. Okay, so we write a minus lambda times I, and out of the vector x which is equal to 0. Okay, so if A is a square matrix, then the characteristic polynomial of a matrix A. Okay, so if already we are taking A is a square matrix. Okay, if A is a square matrix of order m by n, then we write characteristic polynomial. Characteristic polynomial of A as a minus lambda I. Okay, we write characteristic polynomial of A is a minus lambda I. Okay, this one is the characteristic polynomial of A. Okay, so see that A matrix means you can take any matrix as a n by n. For example, just for your understanding, I consider matrix A. Let me consider the matrix A as A11, A12, A1n, A21, A22 to A2n. Up to that, AN1, okay, AN2 up to ANn. Okay, this one is a square matrix of order n by n. Okay, so this way you define matrix A. Lambda times I means identity matrix with this lambda. Okay, so n by n matrix means lambda I'll define here. Okay, lambda into identity. Okay, that means lambda into identity matrix means you supposed to multiply lambda to the entire matrix. Okay, so you will get the only diagonal element as a lambda, remaining all element as a 0. Okay, okay, you will get the all element as a 0. So this one is the lambda into I matrix. Okay, so our characteristic polynomial, it says that a minus lambda I. Okay, a minus lambda I. Okay, so what our characteristic polynomial say that a minus lambda I which is equal to 0. So you supposed to take the determinant. Okay, for that what you have to do you have to you have to subtract a minus lambda and then find out the determinant, and the roots of this determinant, it will give us the characteristic or eigenvalue of matrix. Okay, so how a minus lambda I look like? Let me write this one. So we are taking its determinant. Okay, so write down it into the determinant. A11 minus lambda I. Okay, a minus lambda I means we subtract corresponding elements. Okay, a11 minus lambda I, a11 minus lambda I. Okay, after that a12 minus 0, a12 only, a1n minus 0, a1n. Okay, okay, a21 minus 0, a21, a22 minus lambda, a22 minus lambda, up to a2n minus 0, that means a2n only. Okay, up to this last element, an1 minus 0, an1, an2 minus 0, an2. Okay, and up to ann minus lambda, ann minus lambda. Okay, this one is our characteristic polynomial. Characteristic. Okay, we have to find out the determinant of this matrix. Okay, once you find the determinant of the matrix, you can easily define the value for lambdas. Okay, and these are the characteristic root or eigenvalues of our given square matrix A. Okay, this is the actually method that we define characteristic root or eigenvalue. Okay, the root of a characteristic equation gives eigenvalue or characteristic or latent root. Okay, so we have some of the standard characteristic equations that we use to find out the root of our or eigenvalue of our matrix. Okay, so we have some alternate method also. You can define a minus a lambda I as some another way also. Okay, yes, so consider that A is a square matrix. Okay, A is a square matrix of order 2. Okay, let me write A is a square matrix of order 2, A11, A12, A21, A22. I want the eigenvalue, okay, for this matrix. So you can find out the eigenvalue by A minus lambda I into 0, or which is equal to, you can write a characteristic polynomial as, okay, lambda square minus, okay, lambda square minus addition of a diagonal, that means trace of matrix, trace of A, lambda square minus trace of A. Trace of A means A11 plus A22. This one is the trace of matrix A. Okay, you can add the diagonal minus lambda. Okay, lambda square into trace of A, lambda. Okay, so you can multiply lambda to the trace of A, plus you have to find out the determinant of matrix, determinant of A, which is equal to 0. Okay, this is the characteristic a polynomial or characteristic equation. So you can find out the root of this equation, you will get the eigenvalues. Okay, lambda 1 and lambda 2. Okay, make sure that trace of A means you need to understand A11 plus A22 is the trace of matrix A. Okay, yes, so you can increase the order of matrix like a 3 by 3, 4 by 4. Okay, so if matrix of order 3, then you have to make it a lambda cube. Okay, you have to make the lambda cube here, and after that, so this one is for only 2 by 2 matrix. Okay, this one is for only 2 by 2 matrix. Okay, so if you have 3 by 3 matrix, okay, let me define for 3 by 3 matrix. If it is a matrix 3 by 3, then you can take A minus lambda as 0 as your standard form for finding the characteristic polynomial. Okay, so you can use this one, not a big deal. But if you want the polynomial equation, okay, so in such a case, what you do, as a matrix of order 3 by 3, you take lambda cube here. Okay, lambda cube minus trace of that 3 by 3 matrix. Okay, trace of, consider the matrix is a 3 by 3 matrix is a. Okay, trace of that 3 by 3 matrix into lambda square. Okay, after that, plus minus, again here you have to take the plus. Okay, so after that we want the principal diagonal element. Okay, sum of, we want the minor of principal diagonal element. So minor of principal diagonal element, minor of principal diagonal element. Okay, minor means what is the minor of this one, you have to take 2 by 2 1. Okay, so this one is the minor of principal diagonal element, lambda square. After that you write a lambda. Okay, lambda cube minus trace of A into lambda square plus minor of a principal diagonal element into lambda minus determinant of A, which is equal to 0. Okay, so this one is a characteristic polynomial or characteristic equation for 3 by 3 matrix. Okay, so you can extend this one for 4 by 4 matrix and so on. Okay, but we supposed to know only for 2 by 2, 3 by 3. These are mostly important over here. Okay, these are the two standard remark, guys. You can remember it for finding the eigenvalues. Okay, that one we need it. Okay, yes, so there are some standard results for finding the eigenvalues. Okay, so let me write, okay, for some of the standard matrix and their eigenvalues. Okay, yes, so for example, if we have like a triangular matrix, okay, like upper triangular, lower triangular. Okay, let me write the one remark, upper triangular, upper triangular, lower upper triangular, lower triangular, diagonal matrix. Okay, that means upper triangular matrix, lower triangular matrix, diagonal matrix, all are having diagonal element. All are having diagonal element as eigenvalue. Okay, so for example, consider that I have 1 2 by 2 matrix which is upper triangular, means below diagonal element 0. Okay, like this one. So eigenvalue for this matrix is 1 and 2. Okay, that means upper triangular matrix as matrix is having a diagonal element as eigenvalue, lower triangular matrix is having a diagonal element as eigenvalue, or diagonal matrix, only the diagonal element present, that matrix is having diagonal element as its eigenvalue. Okay, that means and one more, degree of a characteristic equation. So degree of a characteristic equation, how much it is here? It is a 2, and which is equal to order of the matrix. Okay, what is the order of matrix? 2 by 2, obviously degree is a 2. Okay, for 3 by 3 you will get the degree 3. These are the basic concept, guys, you need to familiar with. Okay, so we want some more properties for eigenvalues, okay, that we are going to learn, okay, subsequently. So that's it for our today's lecture, guys. Some of the important properties for eigenvalues and eigenvectors and subsequent point we are going to learn into our next lecture. Okay, that's it for our today's lecture. I hope you all have understood everything here that I taught in my today's session. Okay, so even after, guys, if you found anything difficult, confusing, let me know in comment section. I'll come up with the similar videos. So thank you everyone, thank you for my today's lecture. We'll see next point in our next lecture.